All right, welcome to another lecture for algorithm patterns and practice. Today we'll be looking at the queue and the cousin, the deck. I had a joke about them going to Thanksgiving together, and no, I'll just skip that. Anyway, today the queues that we're going to be talking about are strictly FIFO queues. We'll talk more about this type of access pattern that stands for first in, first out as a queue. Just note that I looked for other material online, not only on LeetCode but other books. Most books and lectures don't just have something just on FIFO queues. They're usually paired with stacks or something else. So just note that when you look at proms on LeetCode, they're actually going to be hard to find. You'll find better solutions for proms that are tagged with the queue tag that I've looked at, so it's actually hard to curate proms. Nevertheless, there are some, and this is kind of a lecture that prepares us to look at breadth first search later on. There was a little bit of work that I recommended before starting today's lecture, and it's number 933, number of recent calls, but don't worry, we'll go over it as well. But let's first off, and let's just motivate queues a little bit. And we'll talk about some real-life applications. And you know about queues yourself because you've been at a grocery store, you've been stuck in traffic before, and you've waited for a bathroom stall to open up, maybe at some place, a theme park, a gas station. But queues are also part of hardware, distributed systems, and they're also used as components that serve as the backbone of services that you really use and love every day. And these queues, they ensure an ordering of first come, first serve. Let's see an example of that. One of the ones is a scheduling algorithm that's used in operating systems. And a CPU is one piece of hardware that has to juggle a lot of processes, right? So you'll basically have one CPU, and basically these things process instructions, right? But the amount of processes you have might be somewhere around thousands, right? 2,000, 3,000, somewhere around that. You can check on your operating system for just a list, or a command line tool, I mean. But a lot of programs, how does one CPU run so many different programs? It's because they all basically do some kind of scheduling algorithm revolving around sharing time, right? So you can kind of imagine this queue, right? So a new process comes in, they're all numbered by some sort of ID, right? ID 23, maybe this is ID 75, and basically processes get scheduled in, and then the CPU just there's something that takes this process off of the queue, and then all the instructions run on the CPU, right? That's just one scheduling algorithm. There's a lot of different ones that exist that you can find on Wikipedia or elsewhere. But that's just one example of where a queue gets used, right? So this is basically first in, first out, because the first thing that gets queued, first thing that goes into the queue, is also the first thing that comes out of the queue, right? Just like a line. Another example that I am not well suited to give you total details about is in networking. All right, so basically in computer, go ahead.
This part I know more about because I'm in networking.
That's great. Yeah, do you want to tell me more about these things? Because I read a little bit about it on Wikipedia, and there's buffering that's used for packets, but other than that, I don't really know too much about it other than that. Well, yeah, anyway, they hold data packets en route to their next destination, right? So buffering is a general technique, and in networking it's used a lot, especially when networks become unreliable and data needs to be resent again and again until a sender and receiver essentially kind of agree on that. And there's different algorithms that do that. But that's all I'll say about this. Another way that queues that you'll see in real life is something you might be familiar with, if not now, then one day, is in this thing called Kafka. It is a streaming platform, but it is also used as a message queue. We won't touch on what the difference between these two things are, and to be honest, it's actually very fuzzy these days because a lot of these services actually blend both of them. But the primary idea is that you have a bunch of these might be like different app servers, right? So say the different app servers basically have invoices, right? But these invoices need to be sent out to different vendors, right? So you can imagine a company that has a bunch of invoicing that they need to send out and bill people for, right? So there might be some jobs that happen internally into the system, and what this allows is a decoupling of producers and consumers. So basically, instead of like talking directly between the producers and the consumers, what you can do is actually the producer, all it knows about is where the queue is at. And all it does is it puts in a piece of work, right? And when a consumer is ready and online, it just takes a piece of work down, right? So in this kind of way, you can actually arbitrarily scale the consumers and the producers separately. So this is used a lot in distributed systems when you need a decoupling between the producer and the consumer. It allows you to have some scalability control that's independent. There's a lot of other uses for queues as well, and uses for Kafka, but we don't need to dive into like everything right now. So this is one popular way. Kafka tends to be also very performant. And it's not also just one queue, it is also a cluster of many different queues as well, and it works really well with whatever types of drives you have available. So typically, like even if you have cheap hardware, Kafka can run pretty well on it because it has a sequential access pattern. All right, don't worry too much about that, but in general, the idea is you want to allocate time to do the work that you can't get done all at once, right? That's basically the general kind of use case, even between operating systems, networking, and even this model right here. There's just a lot of work to get done that you can't get done all at once. And sometimes, even if you can get it done all at once, you might not want to. There are things like timers that are used in games, or even in your own browser, just in any type of Web 2.0 application. Gmail probably being the poster child of Web 2.0 and the single page application, pretty much. JavaScript runs, it has a stack, but it also has an event FIFO queue. What this means is that there's different input events, right? There might be network events such as like, oh, you downloaded something, right? The download completed. Or a timer completed where, some sort of animation happens with, maybe like a hamburger menu expanding and having some fancy animation. So a lot of those things are controlled through an event loop. And this isn't just in JavaScript, it's also used in different places where you have input events. I wouldn't be surprised if you found this happen a lot in video games, because that's actually where I learned about one of these patterns as well. All right, the final application that I'm going to touch on in real world is breadth first search. We might actually cover this a little bit today, we might not, but I believe that breadth first search there's enough material to cover for more than just one lecture on it, so that's why I'm saving it. In the background, you'll see a GIF. This is you basically expand by looking at frontiers, and the reason why this fits a queue kind of access pattern, or first in, first out, is because you look at the next frontier in order to expand. So where my mouse is right now, the next thing that would be expanded upon is the frontier, right? So this is different in a contrast with depth first search, which uses this data structure called a stack a lot. We'll talk more about we'll compare and contrast breadth first search and depth first search in another lecture, as well as stacks more formally. But that's basically like all the examples that I have right now. I'm sure there's others you'll find in the real world. But so how do we power all these different types of applications, and how are those design decisions made? Those are really big questions, but I'm only going to touch on a small piece right now. A lot of how these things are built is just by understanding, right, the characteristics of the type of data structure or the type of strategy or algorithm that you use in order to break down problems. And for a queue, you can really just think about this as a special case of a list where we have the constraint of basically FIFO, where basically elements are ordered. The first thing that comes in is the first thing that comes out, just like that happens in a grocery store line, right? So let's look a bit more about that and see a diagram. So this is the queue, right? So just some terminology is when you enqueue something, that is something that that's just another name for adding or inserting. These are just synonyms, okay, when we look at a queue, but they're specific to a queue. And dequeuing is just, you can look at it as pop. You can also look at it as a delete. But usually when you delete, you actually get the value of what's deleted. So that's basically it. If you think about it, when we talked about linked lists, or even like an array could be like a naive queue that you can think about. There's really nothing more special to it than that, right? You have the back of the queue and you have the front of the queue, right? You put things at the back of the queue, things come out during the front of the queue, just like when you're at a line, right? Waiting for something with a bunch of people. It doesn't really matter in the diagram which way is forward and which way is back. You'll just see it drawn differently, but it'll be labeled front and back. Just to briefly contrast this with a stack. So a stack, the access pattern is actually last in, is actually last in, first out. And you can see this because like A gets put in, right? And then B gets put in, and then C gets put in. But if we want to pop something off, we can only pop from the top of the stack. So in stacks, we have this terminology called the top, and I guess we also call it the bottom. We don't really call it the front and the back. I don't know why. But queues have fronts, and they also have backs. But stacks have tops and bottoms. Traditionally, we look at stacks vertically, and I guess queues, we look at them horizontally. So just keep that in mind. First in, first out. If we put in F first, if we wanted to do a dequeue, we would then dequeue the F. The F would be the thing that comes out, and then the queue would be empty. In this diagram, we enqueued F, then we enqueued, wait, sorry, I did that totally wrong. First you enqueue A, then you enqueue B, then you enqueue C, D, E, and F. And the first thing that came in, remember, is this A. So it's the first thing that comes out. So A gets dequeued first, and then it's B's turn, and then C, and then D, and then E, and then F. So pretty simple. In a stack, it would be basically reverse order, right? So F, and then E, then D, then C, then A. Then B, then A. Right. Hopefully that's straightforward, but feel free to ask questions otherwise. All right, but how do we do this in code, right? It's one thing to see it in a diagram and to make intuitive sense of it, but it's quite another to be able to actually use this idea to start actually implementing. And in Python, it's fairly simple. So if you bring up just Python, just in your terminal or command line, you can start using a queue this way. We've talked a bit about this before in the linked list lecture, but basically to use a queue in Python, you actually use a deck. A deck, I'm not sure if we covered this, but we'll look at a little bit about decks. I have slides on it. Is basically a queue but also you can access it in the way of a stack. But we're just going to use it as a queue for most part of this lecture. So when you try to add something, right? So our queue now is empty, right? It's just like an empty list. And then when we append to it, right, we append this 1. So now we have a 1 here. We append a 3, and now we have a 3 here. And when we do this append, we do append 2, right? That's this line. And we have a 1, 3, 2, right? That's what the deck shows us now. So this adds an element to the right end. There's synonyms for this, but different languages are going to they just use different words for your queue. So just be aware of that. If you're not using Python, you're not going to be using something called append. You might be using enqueue or push or something else. All right. Finally, when you want to remove something, you're going to be looking at pop left. This is a deck, so there's actually also a pop method, which pops from the right side. So if you popped, you would actually get 2, right, from this diagram. But don't worry about that right now. We're doing a pop left, which means that we're taking stuff from the left side, and that's going to give us our, whoops, not a 2. That gives us our 1, right? So if you pop left in order, right, take away 1, and then you pop left again, then you take away 3, and then you pop left again, and then you take away 2, and if you print out the queue, it's going to show you that you have an empty list, basically. So hopefully all that makes sense. Next step is, well, what if you want to search? Python actually has an API for you to search. I believe it is actually get. Like you can actually do get like 1, and it would be like in the queue, this is the 0th element, this is the first element. So, sorry, I didn't like read through the API, but it either gets the first element or it gets the element that matches this value. I forget. But searching is not in general supported from a queue API. This is O of n performance because you do a linear scan each time, right? You compare against each thing that happens, or you just march forward your pointer until that index, and then you remove it. If you do need to keep track of elements, use a separate data structure when you care about the performance. All right, so peeking. Peeking is not an essential operation, but it is basically, you just want to get the element without deleting it. So the way you do that in Python is actually just element access. You can just specify the index. So this is the Python idiom for getting the last thing. You just go -1, and you kind of think about this index as wrapping around. So this is the last, and this is the first. So this is just grabbing the value. It's like no mutation happens. Right? Other languages will actually have a peek method, right? But this is Python, and I looked at their API, and they don't have something like this. So you just use the typical index access. That's all it is. All right, so what are some of the strengths of these queues that we've seen? Well, it's got an O of 1 peek, insert, and pop. And when that fits your access pattern, that's really great. The elements are also ordered the way you put them in, and this is how we see that it operates under the principle of first come, first serve, right? It doesn't mean that all the elements will be acted on quickly, but it just means that all the elements will be acted on in order, right? So CPU could actually, like, I don't know, spend a lot of time on one process, but then not give enough time to some of the other processes. It would still be in FIFO order because the elements would still be processed in order. For DEC, keep in mind that because you can operate from the right-hand side as well, right? So a DEC, you can basically have this access pattern where, you know, a queue would just be this way, right? So you have the back, you put things into the back, you get things from the front. A DEC, you can also, right, just put things into the front and take things out from the back. That's probably why Python just decided not to have a dedicated queue class, because decks basically do everything that queues can do, and they only really need one API for it. Or at least I think that's why the design decision happened, of why Python doesn't have queues formally. And it makes sense. All right, where would you not want to use a queue? Queues are actually pretty specialized, so it's kind of easy to see. Don't use them for searching. That's O(n) performance. For general range queries, they're also not good, and they're not good at dynamically reordering data. For dynamically reordering data, tree-like data structures are often used. For general range queries, trees are also generally a pretty good candidate. There is one special case where I think we do talk about that. There's something called a monotonic queue, or stack, or deck. There's one problem where I'll touch on this idea, and it's a way to find the max or min within a range in O of 1 time. We'll touch a bit about on that, but in general, it's not good for range queries. Also, just note that they have really specific use cases, right? There's a reason why LeetCode doesn't have really good problems. I think it's just in general hard to find problems where you need to use queues exclusively. And to enforce their usage, you kind of need to really care that data has to be processed in a specific static order. But in a lot of problems, it's also possible to use two-pointer techniques or just a sliding window pattern that just uses pointers, right? So queues are very special in their use case, but when they are used, they're very powerful. I'm going to briefly touch on variants, and this is basically the part where I'm going to speedrun through a bunch of these slides. We're not going to talk about priority queues, but you can imagine in an ER room, in a doctor's office, you do not want to process in FIFO order, right? You want to process people by triage, right? Who's hurt the most, who needs help immediately, right? So you'd use a priority queue in that type of case. Yeah, not going to touch too much about on that. That's implemented usually over a tree. There's also circular queues that can be used for, in this diagram, it's for something that takes input events, right? And then you buffer them in so that you can track how the mouse or the keyboard input should respond next. There's often a read pointer and a write pointer. Don't worry about that. It's also used in game development. It's one of the patterns that you use to save time and make things performant, because in video games, you really only have about 16.6 milliseconds per frame if you want to run at 60 frames per second. This is a way, circular queues allow you to reuse objects to save you time from deleting and creating objects, but we don't need to touch on that. Queues can also be used, can be implemented with linked lists, or also just a plain array with a fixed size. I believe one of the homework practice problems helps you explore this a bit more. There's bounded queues where a queue might have a fixed capacity or not. And here's decks, probably more important to go over. Just like before that I showed you when I drew out, you can basically do the operation of putting things in or getting things out from either end, right? This is why a deck is often called a double-ended queue, which is how it gets its name, double-ended queue, right? And it's shortened to just deck. You might also see it spelled this way. Different books spell deck this way, or it's spelled, actually this spells like DQ. Anyway, don't worry too much about spelling. But yeah, you'll see it spelled multiple ways, so don't worry about that too much. You can just do the operations from front or back. That's all it is. All right, let's talk about how you can recognize where to use these queues before we start jumping into prompts. We will have prompts, I promise. So we've talked a little bit about the queue and a little bit about the data structure. Know when to use a queue when the order of events matters. When the order is first come, first serve, or FIFO, generally a queue is a very good candidate. A queue is sometimes even synonymous with this access pattern. And when I say the term access pattern, it's really, at least one way I like to think about the term access pattern is basically how is data accessed, right? How's it used? So if that order is first come, first serve, like in breadth first search, when you have like, wow, that was bad. When you have like a bunch of nodes, right, and you're trying to find a path somewhere, right, the next nodes that you look at have to be in some static order, right? So it's going to be B and C that come next, right? And then these nodes that are on the frontier next. That's why breadth first search can use a queue, but it's actually possible to write BFS just by reinstantiating different stacks. We might see that technique at some point, but BFS doesn't totally need a queue in order to operate. But it's often paired with BFS because of the access pattern is the immediate frontier. All right, another pattern that queues are often part of, even if they're not explicitly talked about in that context, is the sliding window pattern. We haven't talked about the sliding window pattern too much. We will talk about that eventually if I make enough lectures. But it is the spirit of the sliding window pattern. So often in the sliding window pattern, you'll have an array of elements. Who knows, maybe you have 10 to the 9th many elements if it's a huge array. And you usually have a left pointer, and somewhere you have a right pointer, right? And basically when you have, in a sliding window, basically you'll have to move the left pointer at some point, right? That's how you slide this window along, right? The right also moves. So at some point you also have a new right and a new left. You can model this type of access pattern as a queue because you put new things onto the window, right? But the things that are removed from the window are when you slide left, right? These elements have to come off. So don't worry about this too much if you haven't seen sliding window before, but if you have, this should look very familiar. So these would be dequeuing, and this would be enqueuing. So in every sliding window pattern, even if a queue isn't used, the access pattern is basically FIFO, right? So keep that in mind. Some sliding window patterns actually will use explicitly a queue. I think we'll see one problem like that today, and I'll show you about monotonic queues as well in that problem. Closer to real life, use queues when you really need to hold on to data that you maybe don't want to process right now. They're sometimes synonymous with buffers or even buffering something. They basically hold data, right? That you just can't do all at once, or maybe it's not good to do right now. And that's basically kind of all the things I thought about that can help you recognize when to use a queue. I have these things called essential problems, but they're really in quotes because I don't think they're actually essential, but they're really good practice. All right, now I'm going to do a few problems, and I think we're good on time for me to just go through about 3 of them. If we have time, I'll go through 4 of them. But basically, here's like 4 problems. One of them is not explicitly, you don't really need to use a queue to do BFS. That's this one. I do want to go through these 2 problems and this sliding window maximum problem, and we might do this problem. So we'll see how time works, but yeah, this is the order I plan to do things in. Feel free to chime in and interrupt me if something doesn't make sense. All right.
What does BFS stand for again?
Great question. I probably should have written that down on the slides. So BFS stands for breadth first search. Yeah. You might not have taken discrete math, but this is covered in that class, but I'll be going over probably next lecture. if you're not familiar, it's kind of like what I was illustrating a little bit earlier. When you have a node and you want to like find all, let's say you want to find all the nodes of a graph, but you only start with one node where you are right now, right? Maybe these are islands, and you know you have like a little boat, and you want to go to all these other islands. I guess maybe a boat and an island isn't like the best example. But anyway, these two islands are probably the first ones you'll look at, right? Because they're the ones closest to this node. And then from there, right, there might be like many other types of islands, right? And which ones should you look at next? Well, at the second iteration, you would look at this one, and also this one. So we'll talk a bit more about breadth first search, but that's what BFS stands for. It's a graph or tree traversal algorithm. It also works when you can transform a problem into becoming a graph or a tree, which we might also see next lecture or some other lecture. But that's the general gist. Just keep in mind it's a graph or tree traversal algorithm if you haven't seen it before. Alright, so this is number of students unable to eat lunch. Alright, so I'm going to give you a minute to read through this problem, just for you to understand it. The problem description is a bit long, and they probably didn't need to word it with all the words that they used. But take 1 minute, read through the problem, read through the example, look at the constraints, and we'll talk about the problem, okay?
To that link, I'm looking in the lecture PDF, and it says can't view file.
Okay. I will just post the links on Discord.
I think the number of recent points, but not the length.
I put it on Discord. I'm going to put all the links on Discord, so we'll have access to that.
Okay, I'm gonna read it.
Okay. I'll set the timer for a minute. Alright, do you want more time, or do you feel like you understand the problem?
Just making sure. So basically, you have a line at a cafeteria. There's two types of sandwiches. If the person at the front of the line, like, wants a square sandwich, and that happens to be a square sandwich on the top, that person will take it and then go to the back of the line. And if that person prefers a circle sandwich, they'll leave it and then go back to the end of the line. Is that what it's saying?
Yeah, basically. So I drew out a small little diagram, right? So here we have students, and here we have sandwiches. Right? So this student prefers a 1, right? Prefers a 1. We're just going to refer to them as 1s and 0s instead of like the type of circular or square sandwich, which I think is ridiculous, but it's a problem. So anyway, so this student prefers a 1, and it's like, oh no, the front of the sandwiches is a 0. So, okay, I'm not going to eat that sandwich. I'm just going to get all the way in the back of the line. So that's what happens here. And so here that student moves. The next student, hilariously, does the same thing. So they also move to the back of the line. So that's what the queue looks like now. And then the front of the line, right? This student says like, oh hey, this sandwich right here, I would totally eat that. So what happens is that, well, this student now just like is gone now, right? They get their sandwich and they don't need to be there anymore. And same thing with this sandwich, right? It's gone. So now what happens is that this student right here, right, looks at the front of the sandwiches line. It's like, oh hey, I don't like that sandwich. So I'm gonna get to all the way to the back of the line, and they're right here. Next student is able to take the sandwich. That's great. And if you keep simulating, you'll see that the output is 0. There are no hungry students in the students queue anymore, right? Okay, so
My question is, the sandwiches are 1 and 0s, and the students are also 1 and 0s?
basically this is the type of sandwich they prefer, and the 0-1 is the type of sandwich available. Yep.
So we have to figure out which students didn't get a sandwich.
It's a little bit more relaxed than that. You only need to care about the number of students that are unable to eat. You don't have to care about which students. But if you did, you would know the answer still. Yeah.
That's what I meant. Yeah, we had to know how many people didn't get to eat, but I thought everyone gets to eat because there's the number of sandwiches and students are like equal, right? Say you have 10 sandwiches, then there are 10 students, or is that not the case?
Let's look at this example briefly. So I'm looking at sandwiches, right? Let's say there's like a lot of 1 sandwiches, right? But here, the students, they all prefer 1s, right? So how many hungry students are there?
There's not equal number of sandwiches. Let's see.
Yeah, so they can be different.
Two people would not get one.
Actually, all of them would not be able to eat, right?
Why?
Because the first in front of the line sees this as a 1, right? And it's like, hey, I don't eat 0s, so it's going to go to the back of the line, right?
Uh-huh.
The next person is going to look at this 0. They're going to say, I don't eat those 0s either, right? And this is going to happen for all of them, right? So actually, when you go through the length of the queue, you'll know that like, hey, none of these students ate. We started out with the same number of students, so we know now that all the students that are left in the queue are going to be hungry.
So only the students are queuing, the sandwiches are not queuing.
The students that are in the queue are not able to eat at the very end, right?
No.
When we just said.
Yeah, what I meant was they can't just skip over the 0 and go to the next one, right? Like, is what I'm asking.
They're not allowed to do that according to the rules, right? They talk about like the top of the stack. I visualized it a little bit, but yeah, that's what they mean. The top of the stack, this is what they actually mean. So yeah.
So you have to write a code. I see your code and the on the
Yeah, I found that live explaining and also coding actually takes a lot of brain power, so it actually helps me to have notes up. But if I do that, you also don't get to see my mistakes. So Yeah. I should just make mistakes.
Yeah, I did see that. I didn't get to see it for long, but I did see that you first define some things. So like you define, I believe you define sandwiches as students.
Yeah, so I wanted to characterize the problem so in this problem you actually, I think you can use some sort of counting argument and math. I think that's how I wanted to do it at first, but I wanted to illustrate cues, at least to show you how to use them, how to think about them, right? I think that's more important than actually like doing the problem. It's just getting a handle on like how to use these things. Yeah, that's what I'm aiming for here. So even if you can use some sort of counting argument or some sort of mathematical argument, I'm just going to focus on cues. So, all right, when we illustrated like these students moving to the back of the queue, that to me looked like classic queue behavior, right? This looked like classic FIFO behavior, like this pattern of, oh, only the front of the queue gets to make a decision, right? And if something doesn't work out well, they go to the back of the queue, right? This is classic FIFO behavior, and it should make you think about a queue immediately. Also, students stand in a queue, which is another keyword you can look out for. But yeah, so let's look about how we can simulate this in code, even if it's not the most efficient way. All right, so
Can we say number of sandwiches equal to the number of students?
what would we say about that? So we can get the length of sandwiches, right? And we can also get the length of students.
They're equal to each other.
Well, as we saw before in this example, right, even if the number of sandwiches and students is equal, all the students might actually go hungry, right? It's also possible that the length of the sandwiches and the length of the students is equal, and there's no students that are hungry, right? Because maybe you only have one sandwich type and it matches the preference of all the students. So here we have 1, 2, 3, 4, maybe 5 sandwiches. And we also have 5 students, right? Here, in this case, no student goes hungry. Right? All of them just take the first sandwich and then just leave the queue, right? They don't go back to the end. So I think we need to do a bit more than just relating the number of sandwiches and the number of students. We actually do need to care about how to process them in first in, first out order. Does that make sense?
Yes, I don't know the code for how to process them.
Okay. Well, let's illustrate that a little bit. Or you can code along with me. So what I'm going to do is I'm going to have this thing I'm going to call a students queue. The deck is already, collections is already imported in LeetCode, so you can just call it deck. And for the constructor for deck, you can actually pass in students. So here right now, if I print the queue of students, I should be able to get something. I'm also going to just return an integer, just because I know that this function expect is typed to return an integer. Otherwise, it'll throw an error, and I don't think it even gives me the printout. But yeah, so that's my students queue. You can see this in std out. This is my deck, right? And this is this test case where there's 3 students. There's 3 1s, 2 0s, and 1 1, same as in the deck, right? So we've created our queue, right? Now we are able to do this type of processing. But now we want to look at the top of the sandwich stack.
Yeah.
And the way I'm going to do that is, go ahead.
Should we do the same thing for the sandwiches?
For the sandwiches, we could use a queue, technically, we could, but I'm just going to use pointers because we don't really have to care about that. If you think about it, if you just access the sandwiches as a list, and you only care about the front thing, no problem. If you cared about using this as a queue, you can also do that. But I'm basically just going to use a simple for loop. Since I don't need to re-enqueue anything to the back, I think a simple for loop is just going to work. So I'm going to loop through now using that for loop. So for sandwich in sandwiches, right? So if I printed these all out, this would start with 1, then 0, then 0, then 0, then 1, then 1, right? Just because that's our test case, right? So that's what I'm doing that in this for loop. So what I'm going to do now is while students queue, and I care about the front, so, and while the front element does not equal the sandwich type, I'm going to do what? I'm going to move that student to the back, right? So I'm going to append to it, but what am I going to append? Well, I have to pop something off of the queue. So the students...
How do you know the front element is 0? Because you put 0 in the bracket.
Oh, this is just element access. So the front of the queue is not necessarily 0, it's just that this is the 0th element, right?
Oh, okay. It's always going to be the 0th element. Got it.
Yeah, and this is the negative, this is the -1th, or the -1st element, which would be the end of the queue. This would be the first, and so on and so forth.
So basically you're saying that if the number in the queue for the students don't match the first number in the sandwich queue, then append and pop left.
Yep, that's basically this part where if we have a student that's right, let's say this was a 0, right? And this student looks at this, right? This is the front of the queue, right? This is the 0th element of the deck. And hey, we grab the element, the value is 1, right? So this is 1 not equal to, let's say, the sandwich, which is 0, right?
Yeah.
So these aren't equal, so we move the student to the back. So we pop left, yep, and we just add it to the back.
I see. Got it.
Cool. There might also be a case where, you know, we don't want to go into an infinite loop, right? Because if you eventually run into a case where things are, everything is, well, yeah, in this case, you would run into an infinite loop here, right? Because 1 is never going to be equal to 0, no matter how these students are ordered. So we have to care about that. And I'm just going to do that in a really... go ahead.
What else?
This is a while loop, so we'll probably need to find a way to have a break condition, right? When you write else, you need an if. A while is sort of like, yeah, a very continuous if. So we'll need to find some sort of break condition. And the type of break condition that I'm going to go for is just a really naive one. If I've looked through all the students in the queue, then I know that I know I need to stop, right?
Mm-hmm.
I also stop, of course, if, you know, they match, right? But let's handle that infinite loop case first. So I'm just going to keep track of the count, right? I've seen 0 elements, and then in this while loop, once I've done one comparison, I increase the count by 1, right? So I see the 0th element, so count is 0 starting, but then I've seen count is
count is the index.
Count is how many elements I've seen. So maybe I'll just name this to students seen, right? The number of students seen starts at 0, right? Because I've seen nothing for this sandwich so far. Right? I only care about the current sandwich. And if I've seen all the students, then I know that we're just going to have an infinite loop otherwise. So I need to break. So I'm going to break that while loop by adding a condition. As long as students seen is less than, let's say, the length of students queue. Right? This way, once I've seen all the students, the amount of students I've seen will equal all the students, right? And at this point, I'll break from the while loop.
What is it less than and not equal?
You can do it both ways. So you could do it as a not equal if you want. You can also do it as a less than.
No.
So now let's say we broke out of the while loop. There's two cases where we break out of the while loop, right? So if the students seen is going to be equal to length of the student's queue, we can just, well, we can break, right? Break out of the entire for loop, and we can return length of student's queue, right? Because the amount of students left in the queue we know are just going to be hungry. All right, so that's that infinite loop case, but let's just by hand test things out. Well, what if things like go smoothly? What if on the other hand, the other extreme, a student is able to eat? So let's say, so for this current sandwich, which is a 1, right? The student seen is 0, and it's 0 is less than all the students in the queue, and this sandwich is actually equal, right? So that means this while loop gets skipped. So we don't care about this while loop at all. But notice that we've done nothing to the queue, right? We need to actually dequeue it. So we should make sure to do that.
Else?
Yeah, we can do an else, but we also have a break here, meaning that whatever we type in here will happen if this condition is not true.
Oh.
So you can write the else, but you also don't need to.
Or do another if statement.
So the code right here will work fine, but if you want to have an explicit else, you can also do this, right?
Okay.
But when you break, right, this means that you stop execution from the for loop and you jump out. To us, as humans, we would see that code execution return on 9, come back at line 21 to this return statement. But it's going to be the same because this break essentially acts as like, if this is true, none of these statements can happen, right? Line 17 can't happen.
So in this case, the student would take the sandwich and then leave. So is that why you have top left?
Mm-hmm. So this change.
Where does it go?
Just removed from the queue. It's just gone.
Top left is removed.
Yeah, just removed it. We don't add anything back, right? Because the student is able to just go happily and eat their sandwich. Does that make sense?
Yeah, I thought pop left did something else, but I guess not.
It just removes an element. And it removes it from the left side.
On the left side. Okay.
Yeah. Here we do a pop left and also append because we move that element to the right side again, right? But when the student just leaves the queues, just straight up leaves, and takes their sandwich and then leaves, they don't need to be put back into the queue.
Mm-hmm.
Alright, well, it passes for those test cases.
This is not as complicated.
Yeah, I want to start things off easy. I think that's always a good practice. Anyway, I'm going to try and I'm going to comment out this print line, and I'm going to submit this, and let's see if it works.
What I was confused on was I thought we had to do both things, like the student queue and the sandwich queue, but it's nice that we don't really have to touch the sandwiches. We're really just like focusing on the students.
Yeah, you could have actually written this code in a different way. There's only one way to do this problem. Yeah. And I think there's a linear time complexity linear time complexity solution. This is of students times sandwiches. Worst case, right? Every sandwich is going to force you to look through basically all the students. So I think there's a better time complexity for this one, but the constraints are generous enough that you don't have to worry too much about that. And all I wanted to illustrate was just the Q API and just recognizing that pattern. Anyway, that's enough for that problem. Hopefully that was understandable, but you can also probably rewatch the recording if that wasn't. Alright, so the next problem is Dota 2 Senate. When I originally solved this problem, I used one queue, but I find the 2 queue solution to be much more elegant. So I'm going to be showing you that one. So I'm going to give you a minute to look through this problem, and then we'll talk a bit about it. Alright, do you want more time to feel like you understand?
So there's this game, right, Dota, and they're trying to vote on a chain, and there's these 2 parties, one is Radiant, one's Dire, and there's all these like conditions, like banning a senator's right, a senator can make another senator lose his rights, and then there's the other condition, which is if this senator found the senators who still have rights to vote, he can announce a victory. And then they want us to predict which party wins. So I guess the queue there's a queue involved, right? So the queue is like the senator, like the number of senators.
Yeah, so there's the Senate, right? And what's very interesting is that if you look at the explanation, it shows you that the first senator comes from Radiant, and he can just ban the next senator's right in round 1. So in this example, basically, whoever comes from the left side has an advantage, right? So the radiants here kind of have first move. Basically, they get to ban this Dyer person, right? And then this Dyer senator doesn't get to act, right? But the next senator that can act is this Dyer, right? And this Dyer person can work to ban this radiant senator, and then Dyer wins, right? So you're right, essentially there is a type of queue because it's almost like, well, the first one that shows up is the first one that gets to move, right? Gets to basically ban, right? Something that I had to reread a few times is that announcing victory can only be done if all the senators are from the same party, right? So it has to be that all the senators are from the same party in order to win. So even if you can't announce victory when you have like RD, RD, right? You can't just as a radiant decide to win, and the Dyers can't do anything about it. So in this type of simulation, really the most important thing to get right is actually the first rule. Senator can make another senator lose all his rights in this and all following rounds. So I think you got the problem basically correct. So do you feel comfortable telling me how to code?
I can try. So I'm thinking like I'm trying to relate this back to the other problem that we just did. So like in this case, sandwiches would be like the Senate, and the senators would be like the students.
I would say don't worry too much about the previous problem.
Okay.
Don't worry too much about sandwiches and students. Here there's a bit of a different dynamic at play because people in the queue can nullify other people in the queue, right?
So I kind of see like a cutoff of your code. So I can see you put R over underscore Q equals something something, right? And then D underscore Q. So let's start with that, I guess.
Sure. Let me just illustrate one example of how you might try and approach this problem. So let's say you have a radiant person, right? To the right is another radiant person. But what does this radiant person want to do? Right?
He wants to ban.
It wants to ban, right? In some ways, this is a bit of a greedy thing to do. You want to ban the first person of the opposite party that you can, right?
Yeah.
So you want to ban this Dyer person, right? Because it might be the fact that like later on there's another radiant in between these Dyer people, and then they get to like take off the first Dyer person, right? So you want to leave opportunity for that, and the best way to do that is actually just to ban the first Dyer person, right? Because if you imagined you banned this person first, and then this radiant banned this person, then this Dyer person would just ban one radiant person, and I guess the radiants would still win. But it's not efficient, right? So you want to give the best chance possible.
Well, right
So-
now we don't know how the queue looks like, so we can't really say. We have to straight first see what the queue looks like.
So that's an interesting thing. Let me get to that in a bit. So this radiant wants to ban this Dyer person, right? This radiant gets here and wants to ban this Dyer person, right? This Dyer person is going to ban who? Who does this Dyer person ban?
This person has no one next to him. Is the end of the line.
So there's a round-based procedure, right? So the next person who's going to come after this Dyer is actually this radiant right here.
Which like circular?
Yeah, it's circular in a way.
Okay.
Yeah, the voting for this change is a round-based procedure, and there's going to be multiple rounds. It loops back. I'm trying to find that detail. Starts from the first senator to the last senator in a given order. I'm trying to find the line where it just outright says that, but
It says the procedure will last until the end of voting.
yeah, I guess that's what shows that. But anyway, I'll just tell you. Yeah, so this radiant is basically going to be the next one to go, and then it'll be this radiant. That'll be the next one to go. So who should this dire person ban? It should ban this one. So then that leaves this radiant, and it going to bans this dire, and radiants win. So anyway, that's that example. One of the things I posted on Discord was to basically look over that problem, merge two sorted linked lists. And this is actually very similar to that problem if you break it down into using two different queues.
It's been a while.
It has been a few weeks. Alright, so we're going to use the same strategy as merging two linked lists, and this strategy I'm about to show you was not obvious for me to come up with. I actually did it with one queue first, and then used a bunch of counters to count how many dyers were left and what the ban count was. But I think this is more elegant, so this one that I'm going to show you. So essentially what you can do is you can look at this diagram right here, and well, the radiance, right, the RQ, and this is what it's going to hold. It's going to hold the indices. So it holds index 1 and index 0 and index 1, right? 0, 1, 2, 3, 4. The dire queue is going to hold 2, 3, and 4. And basically, if you look at these values, right, you can kind of see like, oh hey, which one of these is going to come first, right? So it's this 0 or this 2, right? Because if they use a greedy strategy, this radiant is going to for sure want to ban this 2, right? So this 2 gets popped off, right? So this is no longer there. But this radiant person, right, should be accessible later, right? And also because they're going to be accessible later in the queue, the dyers should have a chance to ban them. So what happens is that, well, if you look at the total length of the queue, there's 5 elements, right? So logically, the end of the queue would be at index 5, right? We just happen to split things up into 2 queues for better management. So this gets in-queued as 5, right? So now the queue is basically 1, 5. So now this 1, right, this radiant right here, gets compared to this 3 right here. And which one should come first? Well, this radiant should win and be able to ban this dire person. So they just get removed from the queue. And similarly, they get added to the end now, right? And they get added by 5, right? So this dire person that was right here, that was at index 4, right? We know that this radiant person should be over here now to act on their turn. So does 4 win against 5? Yes, it does. So it removes this radiant from the queue. So now you're left with 1 radiant, and this dire person, you know, logically at the end of the queue would be at, like, let's say index 9 now. And now it's 6 versus 9, 6 wins, which is this radiant right here, so then you're done. So that's the entire algorithm.
Well, basically it's kind of like for every RQ, you look at the element and then you pop left for DQ, or the DQ.
So if vote equals the radiant, what we're going to do is, so first of all, I'm going to populate the queue. So let's see. I actually care about the indices, right? So I'm going to use enumerate.
Top right.
I'm just going to fill in the indices first. So I'm just populating, and that means I'm going to add, right? So in Python, that would be append. So I'm just going to say rq, add, else. I'm going to have my dir-q, and I'm just going to append the indices. I like to print things out just to make sure I've set up my data correctly. And for that test case, that was actually rrddd. Let's see what that is, but I also need to print out a string. I'm just going to return radiant because I just don't want to see an error.
What does enumerate do again?
You can check the Python API, but basically I think it creates an iterator over the Senate, and basically you have a tuple now that you can access. This gives us the index of the character, and the vote is actually just going to be an R or a D. So the Senate, remember, is just a string. It's going to be RRDDD in this example. So enumerate just gives us the index paired with the value. And when we looked at this algorithm right here, just walking through, all we cared about was the index. So let's look at these two decks. It's 0 and 1, right, for these two R's, and the D's are 2, 3, and 4. That's exactly what we expected. So good. So far, so good. Now, let's do that algorithm, which is basically like merging two linked lists, right? You just compare the front values, and you make a decision. One of them loses. What's interesting is that we actually reappend using the length.
Can I ask you a question?
Yeah, what's up?
When you did quotes, radian quotes, is it because it's already in the Python library? Like, how does it know what radian is?
Sorry, can you point to which line? Is it line 16 you're talking about?
Yeah, like, how does it know that? Is it because it's already programmed or defined earlier?
This is actually just a string. So the output just wants you to return a string of some sort. So this is the dir string, this is the radiant string, right? To make a string in Python, you can like just type in whatever, right? Right, it's just a string. So all I did was like, I know this function signature says I need to return a string. So I just hard-coded radiant because I wanted it to return something. Because I don't like seeing errors personally when I just do a printout. I just like being able to search for the std out.
Well, it can recognize any string.
Yeah, so let's say I return 0. This would be a type error of some sort, and I would get like lots of big red angry stuff, right? And it would not print out what I wanted. Well, actually my print statement's commented out, but if I run it again, oh, actually this while block isn't indented. Pass is just a no-op. You can just put that in. But yeah, it's going to be angry at me, and actually this is an infinite loop. Whoops. I should have just typed in break. So yeah, I guess it does give you the output, and it wasn't angry at me for like returning 0 as a string, but yeah. I just wanted to return a string just to conform to the function signature. Anyway, moving on. So basically one of our queues is, go ahead.
And LeetCode gives us the function signature. It seems like it always gives us that before we start.
Yep. So if you like reset this default code definition, you can confirm, and it's like, oh, here's the template, and you start writing code on line 3. Yep. So if you haven't done LeetCode that much, do a few prompts, try some of the pre-work, and that'll help you get the hang of it. Alright, so continuing on, basically our algorithm should stop when one of our queues is empty, right? The empty queue is going to be the party that loses, right? If the radiant queue is empty, that means the Dyers win. If the Dyer queue is empty, that means the Radiants win, right? Because only one party can win, you can't have a situation where both queues are empty, because one senator always has to win in each comparison, right? So now I'm going to compare the fronts. So if our queue, right, I'm going to get the front of the queue, so that's index 0, is less than dq, and we're also going to get the front, what should happen?
EQ pops to right.
Pop left. We're just going to use them as queues, right? We use append and pop left for a queue. And what happened? Sorry, what was that?
I don't understand why is it to the left, because we're looking at the right one, so the right one disappears.
So let's look at this a little bit. All right, so we have 0 and 1 and 2, 3, 4, right? When we appended, right, and printed it out, this is what we saw. So the front of the queue, right, is effectively all the way to the left, right? Right? So when we access at index 0, this is the left side of the queue, right? So if we were to remove something, right, just straight up remove, we just pop this from the left side. So then we're end up with 3 and 4. Yep. It's a bit hard to get used to without like writing code for it a few times. So just with some practice, you'll be able to see that. All right, though, back to our example. So we made that first comparison, right? 0 wins against this 2, right? We want to add this 0 at 5 now, right? Position 5. So how do we do that?
Append.
Yep, append, right? Because we add something to the left. We need to do something to the left element, right?
The 0 leaves and go to the end of the line.
Yep, not just the end. Yep, it goes to the end of the line, but also importantly, we want to keep track of its position.
Oh, plus
right.
1?
Not 1.
Sorry,
It is actually going to the length of the queue, right?
I plus
because
1. I.
Different letter. Try a different letter.
The last index plus I. I mean plus 5. I mean plus 1.
It is going to be effectively 5, right? In this problem, we represent 5 using n, the length of the Senate, right? We do this because it happens to be the end of even, like logically there's really only one queue, but in how we broke down the problem there's 2 queues, right? So if this radiant was to go to the end of this line, right, it should be at position 5, right? It should be advanced by all the elements in the queue. So that's why we're going to add n. N plus whatever position it's in currently.
Oh.
Right? Pop left gives us that value, which is actually the value 0. So when we do n, right, it's going to be 5.
Oh, okay, I get it. Basically, when we append, that's already a 1. We're already adding 1. So that all of that is 1, and then plus n.
Okay, let me illustrate this a little bit. It's a bit more nuanced than that. When you do the pop left, you get the value, right?
Yeah.
So this n is this 5. This pop left is this 0.
Okay.
So when you do the append, this queue is going to get mutated into 1, 5. If you look back at this diagram, right, there's going to be 5 total positions, right? This radiant needs to happen all the way after everything now, right? That's why we add 5 to the index. So there's both the factor of the position in the queue itself and the index, kind of like the logical index that comes next. So the logical index that comes next should be 5 now, because this 0 became this 5.
Yeah. So basically, the second R gets pushed up, and then the other one goes to the back of the line.
Yep, because we were moved here, you're right. The second argument gets pushed to the left now, right? And this one goes to the back of the line, and we add a value to its kind of like logical position, so it's at 5 now. And we basically, if it happened the other way around, it's the same logic. So radiant Q gets popped left, but the Dyer Q depends doing the same thing if it wins.
It's like symmetric, like you were saying.
I'm also going to print the RQ and the DQ to help you visualize this a little bit.
3, 1, 5, and then 3, 4, 2. No, 3, 4, 3, 4, 3, 4 something. 3, 4, 3, 4, 4. 3, 1, 2, 3, 4.
It's probably best if you had like a pencil and paper and like drew it out yourself. But I am going to print it for you. So with your prediction now, let's just see what happens.
Yeah.
So,
1, 5, 3, 4.
right, because these, right, it's, so you might not have done this problem, but basically you just compare the heads basically of the cues, right? And you make a decision based off of that, and there's always one element that gets removed, that's guaranteed, right? And so you can see like this 4 is going to win against this 5, right? So this 4 now gets logically added to the end of the queue. It's at a logical index of 9 or something like that. But this 9 doesn't win against this 6. This 6 ends up winning against this 9. And there's no more Dyers left, right? The Radiants have banned all of them. And we exit the queue, we exit the while loop because one of them is empty. So if they're empty in Python, this expression returns false. And that's basically the problem. So we broke this down by looking at it as a first in, first out kind of pattern. It's wasn't obvious to look at this as using 2 queues, but I think this is a very elegant way to look at the problem, rather than using 1 queue.
The radiant line, basically.
Yep, for this example case, but there's many other cases. Let's see if I've gotten this. Well, I guess I don't have too many other examples to show you. Yeah, you can also write it with 1 queue. This is an example of how to do that if you just want to keep track of the counts. In either case, the time complexity is, well, basically O of n. So that's that. I do want to give you all a chance for a break. Hi, Spencer. We did these 2 proms. I actually want to go through this prom. It's marked hard on LeetCode, but I think with a little bit of thought on how to use queues, especially monotonic queues, helps you solve this problem, and it's not too difficult, I think, once I show you that idea. I would say maybe read through this problem, and we should probably take like a 10-minute break or something. I'll do this problem, and then we'll come back and let's do some small group work where you can practice. And then we'll wrap it up for the day.
Before we take break, what do you mean by monotonic versus another form of queue?
So monotonic. Let's just look at the word monotonic. let's say you look at a graph, right, and you have a bunch of values, and you plot them, maybe this is the x, and maybe this is the y, and you can look at this piecewise function, I guess. I guess I didn't have to write piecewise. But you can see how it has ups and downs. This is not monotonic, right? It's both increasing and decreasing depending on which sections. But if you looked at it, if maybe you had a different type of graph, right, and you saw it only increasing, even if it increased like differently, the rate of change was different, it's always increasing, right? So this is monotonic. When we talk about cues, there's a property we can maintain. Monotonicity would be that term. So this is a way in which you can get a way to do an O of 1 min or max out of a range using a cue over a window of elements, for example. I'm going to be showing you this technique later, like after the break, but basically, if you wanted to do this problem, you can do this in O of n time and in O of n space. And the basic idea is like, well, out of this window of elements, k being equal to 3, and you want to record what the maximum is. What you can do is actually, with your cue, you can ensure that your cue is monotonic. Basically, your max is always at the left, and basically you store elements that are less than the max to the right. And that's all you do. So let's say you started off with this 1. The moment you saw this 3 come in, you would know that the max for this window is going to be 3 until this 3 is popped. So there's no reason to keep track of this 1. You just pop it off, right? And then you're like, hey, 3 is going to be right here now. You see the -1 come in now. And it's like, well, -1 could be the next biggest thing. Like, I don't know what's here. Like, maybe it's -1000, right? So -1 could be the next biggest thing, but maybe not. So I'm going to just record that right here. But if the next value was like 7, if 7 came in, I would notice that 7 would be the largest value for the entire window. So I compare this to the front of the cue, to the back of the cue, and I'm like, no, 7's bigger than that, so I don't need to care about that that -1, because I know 7 is going to be the max for the entire thing. And I compare, I know it's going to be the max for longer than -1. So now 7 gets compared to that 3, and it's like, hey, 7's bigger than this 3, so the max is going to be 7 for longer than the 3. So you can kind of maintain a monotonic cue because you know that all the elements that are added in have to be less than the 7, right? These potentially could be maxes after this 7 expires. So each of these has that chance. But the moment something bigger comes in, like a 9, bam, all these things get crushed, right? 9 is going to stay the max for longer than all the other elements. So that's the basic idea. And obviously if you had like an 11 and then you had the 7 or whatever, it would just like remove all these elements, right? But that 11 would still stay into the queue. So you can use that idea. Go ahead.
You play this card game called Asshole?
I think I played it once when I was a young man.
It kind of reminds me of this. When you're the president, you sit in a certain spot, and then once you become like the asshole, you go to the back, like to the very bottom. So it's this constant like replacing. Yeah, kind of reminds me of this.
Okay, good. Keep that in mind. Maybe this is a variation on the game of asshole. I'm not sure. Also to like just make sure I got my words right. This is actually going to be a monotonic deck, right? Because the access pattern is not only going to be from the left side, we're also going to be looking at elements from the right side, right? Insert and also extraction from the left side, and also we won't be inserting into the left. Into the left, we'll be inserting into the right, but technically this type of access pattern would be a monotonic deck, not simply a queue. Anyway, we'll talk about this problem once we get back, but read it and keep this idea in mind, and you can probably see how this can be an O of n algorithm already from what I've said. But anyway, let's take a break. And glad you're with us, Spencer. But let's take 10.